Hello, I hope that you have been able to evade the freezing drizzle this morning. And in lieu of being able to answer all of your questions about the homework in person, we'll have to rely on email and this video. So this video I'm going to walk through and help you set up number 5 on the homework. And if you have questions about any of the other problems, then you will just need to make sure that you email me. For number 5, I'm going to take two approaches to the problem. The first approach that I'm going to take is for those of you who are kind of getting bogged down by the mathematics sometimes. A problem like number 5, a ranking problem, as long as you understand what torque is, the variables that affect the equations, you don't necessarily need to go through and do all the math, and like in the second, method, I'm going to draw a bunch of vectors and things like that. I think you can think about it more intuitively and make some sense of it. So let me just quickly sketch out what these 4 pictures look like. For the first picture, we have the wall there, and then attached to that wall there's a rod that is at 30 degrees, and the sign is hanging down from that rod. And this is case A. For case B, the wall is there, the rod is at 90 degrees to the wall, it's perpendicular to the wall, and then the sign hangs perpendicular to that rod. In case C, similar to case A, but there's a greater angle, so now it's 60 degrees. The sign once again hangs straight down. And then in case D, we have another example like case B where the rod is perpendicular to the wall and the sign hangs straight down. But the masses are different in each case, so we should probably indicate that as well. In case A, the mass is 50 kilograms. In case B, the mass is 100 kilograms. In case C, it's 50 kilograms. And in case D, it's 90 kilograms. All right, so my first method is sort of a brute force ranking, I know a little bit about torque method. So we'll start by just saying that we know torque depends on R, it depends on F, and it depends on theta. So let's look at the two simplest cases, B and D. In this case, the axis of rotation, similar for the other two, is going to be this point where the rod is attached to the wall. If the mass of the sign were too heavy and it were to pull on that rod too much, the rod would rotate about those points in green. Same thing for the other two cases. If that's the axis of rotation, then how are R and F defined? F, the force that would cause a torque, which might cause rotation in any of these examples, would be due to the weight of the sign. And the weight of the sign we would normally draw as something like this. I'm just going to extend that arrow up to the end of the rod because, maybe there's a string attached to the top of the block or the sign. And so that block has a tension in it. It's equal to the weight of the block. So who cares about all those other forces? Let's just talk about the weight, which is pulling down on the end of that rod. So here we have mg. And here we have mg. The rods have the same length in each case, and so I've drawn in the forces, but now I want to draw in R. R is the distance from the axis of rotation to the location of the force. So there's R, and there's R. And the angle between R and F, which is this 90 degree angle here and this 90 degree angle there, is the same for cases B and D. And so if R is the same, theta is the same, the only thing that determines what the magnitude of the torque is going to be is the weight of the object, and really not even the weight, because both objects are in the same gravitational field, so G is the same for each. So really it's just the mass of each sign that determines whether it's going to have a larger torque or not. And so for that reason, I know that B has a larger mass. And so in my ranking so far, the only thing that I know is that B needs to be greater than D. The next thing that we might look at is the case between A and C. For A and C, we know that the rods have the same length, right? This is a length R, and this is a length R. The masses are the same, which means when I label my forces, mg and mg, the weights of those two objects which are causing the torques, which might cause rotation, those are the same. And so in my equation for the torque, the only thing that's different between the two is the angle. And I'm going to deal with the picture with the angle and how that factors in, and the challenges of working with that later. But right now I just want to point out that we know when the force is perpendicular to R, we get the greatest torque. And when the force is parallel to R, we don't get any torque. The example that I gave of that is when I push toward the hinges of a door, the door doesn't rotate. It's parallel, no rotation. When I push perpendicular to a door, it opens and closes just fine. And so it should make some sense that if the force is applied perpendicular to the rod, then we get a bigger torque. And when the force is applied more and more parallel, then we get smaller torques. And so in case A, we have the same mass, the same length rod, but a different angle. And in case A, that angle gives us more of the force along the direction that is parallel, right? So if we imagine, mg as being a triangle, I'm going to draw a big triangle that represents a little force triangle for that gravitational force. And I'll do the same thing for the other one. My pictures aren't to scale, so this isn't going to work beautifully, but what I'm hoping that you're able to see is if I grab onto the right end of any of those rods, when they're perpendicular, I have a really big torque, and then as I start to lift up the end of that rod, more and more of the gravitational force is pointing along the direction of R, toward the axis of rotation. So much that if I lift up the rod very far and the angle gets extremely small, almost the entirety of the gravitational force points along the direction of R. And so we're getting smaller and smaller torque as I make that angle smaller. So the next thing that I would point out is that because A has a smaller angle, we get a smaller torque. So that means in case C, you must be getting a bigger torque than in case A. Again, look at C. I mean, yeah, the masses are different compared to B and D, but C, the rod is oriented more like B and D, where we're going to be getting bigger torques because the force and R are perpendicular to one another. And A is more vertical, and so we get a smaller torque. So I know B is greater than D, and I know C is greater than A, but now we need to compare these two things. The next thing that I'll do is I will say that I know B and D, while we already ranked those two, they're going to have larger torques compared to A and C. And so I could align these two sets of rankings in this way. B is greater than D, and I know that those need to be on the greater end of my ranking, and C and A, which we've already compared, need to go on the other end of my ranking, the smaller end of the ranking. The only question is, what is this comparison in between here? And you might be able to immediately suggest that it's greater. And the way to do that is to just say that sine theta has the biggest value when theta is 90 degrees. And for cases A and C, the angle between R and F is becoming less than 90, which means that we're going to get something that's less than 1. And so ultimately, whenever I multiply a number by something that's less than 1, I'll get a smaller torque. And so to rephrase that, something which I said kind of quickly, this angle here between R and F, or this angle here between R and F, so I'm drawing in the angles between these. For cases B and D, they're 90 degrees. For cases A and C, by alternate interior angles, we have for case A 30 and for case C 60. Those angles are going to give me something less than 1 for the value of sine theta, and when I multiply r times f times something less than 1, I'll get a value that is smaller than if I just had r times f, which is what I have in cases B and D. So with that fact and the fact that in cases B and D we have masses of sines which are much heavier than in cases A and C, you should expect that there's a greater than symbol between those two sets. And so my final ranking is B is greater than D, is greater than C, is greater than A. If you were able to understand that first go through the problem, that's really good, but I do strongly recommend that you make sure you know how to do it this way that I'm about to tell you, because sometimes we're not just interested in ranking towards torques, we're actually interested in figuring out what is the torque. And so in order to do that, you need to know how to compute these things, not just compare them to one another. And so what I'll do is I'm going to draw a generic picture of what we were just staring at. We've got a wall, there's a rod coming out at some angle theta relative to the wall. The sine hangs down like this. We have the gravitational force which is pulling on the end of that rod, which I'm just going to label F. And then we have the axis of rotation, and then R, which goes from the axis of rotation to the location of the force. There's R. And previously, when I've written a torque equation, I've said torque is equal to Rf sine theta, or R perp times F. And so what do I mean by those two things? How would we use either one of those in this case? Well, in this case, there's an angle that's given for cases A and C, which is the angle between R and the wall. Now, one thing you should be asking yourself is that the angle that I'm allowed to plug in to this torque equation, or is that a different angle? Sometimes they give us an angle, but it's not necessarily the one that you want. The angle that we want is the angle between R and F. And so the angle that we want is this angle here, right? The angle between R and F. And so if I knew what the length of the rod was, and I knew what the gravitational force was pulling down on that rod, and I know what the angle between those two are, then I can calculate the torque in each case. If there's a situation where you don't know R, or you don't know the angle or something like that, then there are other ways that you can go about this. One way that this is commonly done is, as given by the equation above, we use R perp, which is the distance from the axis of rotation to the place where the force is applied. And so what does that look like in this picture? It looks something like this yellow dotted line. So notice that yellow dotted line goes from the axis of rotation to the line of force, right? So it doesn't exactly touch the place where I drew the force as being applied, but this is that perpendicular distance from the axis of rotation to the line of force. And you might be able to imagine that I could have also drawn that yellow dotted line at the top of the rod, where it starts at the upper right end of the rod and goes to the wall. That would be that same perpendicular distance. And then after drawing that, if I knew what that distance was, then I could use the same gravitational force in that perpendicular distance, and the product of those two would also tell me what the torque is. Another way that we have defined torque is, ignoring the fact that we're dealing with these angles here and just saying, I know that only the perpendicular part of this force relative to R is going to cause any rotation. And then saying, what is that perpendicular part of that force? So here's a triangle where this part that I'm labeling in the upper right is the force that's perpendicular to R, and then this part down here is the force that's parallel to R. And then of course the hypotenuse of that right triangle would be the gravitational force m times g, which I originally drew in red. And so, maybe a second or a third way of going about this is to figure out what is F perpendicular. So keep R, don't find the perpendicular part of R, but find the perpendicular part of F that causes the rotation. This is a slightly more tedious way of going about this, because in order to determine what F perpendicular is, then you need to know how to express F in terms of something in this triangle. And so what I'll point out to you is that if F perpendicular really is perpendicular to R, the green line, then this angle that I'm drawing in yellow is 90 degrees. And if I labeled part of that 90-degree angle as theta because of alternate interior angles, the theta there and the theta by the wall are equal, then this angle, which I'm now drawing in blue here, is just 90 minus theta. And so if I knew what theta was, I do 90 minus theta, I can find the perpendicular part of the force that is relative to R, and then use that perpendicular part of the force, the whole length of the rod, to find the torque. And so I guess one way you can think of that is, instead of R perpendicular times F, it's kind of like R times F perpendicular. Okay, so either use the whole R, the whole F, and the angle between the two, find the perpendicular part of R relative to F that goes from the axis of rotation to the line of force, or find R times F perpendicular. Use the whole R, but then the perpendicular part of the force relative to R, relative to the rod in this case. I think of these, few methods that I've shown, the one that makes the most sense in this case was the first one that I showed, where we just use RF sine theta. That doesn't necessarily mean it's the case in other problems. It might be hard to imagine, but in this case, I'll just use RF sine theta. So when I'm calculating the torques, I know I'm going to use R times F times sine theta, and I know that the force, even though it's applied in slightly different manners relative to the rod, it always points straight down, and we're always talking about m times g. So R times mg times sine of theta. And I know that the length of the rod and I know that the gravitational acceleration are the same in all four cases. So while the torque is equal to Rmg sine theta, the torque is also proportional to m sine theta. So notice, I'm not calculating any torques. I'm going to calculate what m times sine theta is in each case, because that's the only thing that I need in order to determine the torques. Because as I said, the length of the rod, r, I'm not using r perpendicular here, I'm just using r and f, the whole thing, and the gravitational acceleration are the same in each case. So instead of calculating those, I'm just going to figure out what m times theta is in each case, and then compare them. So for case A, I have m, which is 50, and then sine of the appropriate angle, which luckily in this case they give us that 30-degree angle, which is the white labeled theta in my picture. So sine of 30. And when I do that, 50 times the sine of 30 degrees is about 25. For case B, we have a mass of 100 times the sine of 90 degrees, which is about 100. For case C, we have 50 times the sine of 60 degrees, which is about 43. And then finally, for case D, we have 90 times the sine of 90 degrees, which is about 90, right? Because the sine of 90 is equal to 1, so 90 times 1 is equal to 90. And so notice, I didn't calculate the torques, but m times sine theta is allowing me to rank the torques. And so what do I get? The one that's the biggest is B. The next biggest is D. The next biggest is C. And then the next biggest is A. So the same ranking that I got when I kind of worked through it with some intuition and conceptual reasoning. If you have any questions about this problem or others, please do not hesitate to ask.